Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. I bid to Dr. ARIF. Today we are from group 1. We would like to present to you experiment 5, which is bending moment. Firstly, I want to introduce my group mate. First, my name is Putri Nur Emilia Roslina, and my other group mates are Aliana Suha, Izzatun Nazla, and Nur Farisha Idina. The introduction of the experiment is: first, bending moment is a force measurement that occur when a force is applied at specific distance away from a material, causing the material to bend. A moment is rotating force that happen when a force is applied perpendicular to a certain place for a particular distance. Moment can be calculated by multiplying the distance from the point with the perpendicular force, which is m equal to Fd. The bending moment measure plays an important role when calculating and analyzing the material that require for manufacturing and accurate engineering structures such as equipment and machinery. Next, our objective of this experiment is to measure the bending moment of the material when subjected to different load at different distance. The scope in this experiment is the experiment will be conducted using load ranging between 0 to 20 Newton and the distance between P1 and P2 and the distance between P2 and P3 according to the section of the experiment conducted. The theory of this experiment is: first, a bending moment is an internal force that causes a beam to bend as a result of an external load. Next, bending moment can be appeared anywhere along the beam and represented by a circular arrow. Third one, the bending moment at any given point in the beam is equal to the product of the external force and the distance perpendicular to the force direction. According to this simple drawing, the beam has been cut into two sections. Qx, which is in the middle, is a shear force that acting in the plane, so the moment vector is perpendicular to the plane. As the shear force is moving upward and downward, be it at the right side and the left side of the beam, it will considered as positive shear force. In our calculation, we would like to eliminate the shear force, which is Qx, so we can use our equation moment equal to force times by distance, which is m equal to Fd. For section A, we would like to eliminate the Qx by using the formula negative mx times by resultant force A, Ra, times by A, which is the distance. For section B, we will using negative mx equals to Rb, which is our resultant force at B, times by B, which is our distance of beam B, minus by P, our pressure, that been multiplied by B minus 1. And simplify the equation, we will get negative B times by Ra plus Ra multiplied by A plus B.
This is the experimental setup for bending moment experiment. The first one is base unit, spring balance, 10 Newton loads, 5 Newton load, long beam, short beam, 3 hangers, and gauge. Methodology for part 1. The first one is the beam was set up so that the bearing pin in part B is 300 mm from the left hand support and 600 mm from the right hand support. One load hanger was placed on the middle of the smaller part A of the beam and one on the larger part B, and the third one at the joint just over the bearing pin. And then next, turn the knob until the bubble of gauge at the center and record the initial reading. 10 Newton load was added to P1, the beam was realigned, and the new reading on the spring balance was recorded. Repeat the step for P2 and P3. Then 20 Newton was added to P1, The beam was realigned and the new reading on the spring balance was recorded. Repeat the step for P2 and P3. For part 2, the 3 load hangers were placed as desired. The beam was realigned and the initial reading on the spring balance was recorded. And then the 5 Newton load was added to P2. The beam was realigned and the new reading on the spring balance was recorded. Next, 10 Newton loads were added to P1 and P3 while 5 Newton loads still at P2. The beam was realigned and the new reading on the spring balance was recorded. The experiment in part 2 was repeated by adding 5 Newton load at P2 and 12 Newton load at P3. The beam was realigned and the new reading of the spring balance was recorded. And then 2 Newton load was added to P1 and 20 Newton load was added to P3 while P2 still remains of 5 Newton load. The beam was realigned and the new reading of the spring balance was recorded.
Now let's move on to the result. So for part 1, we took a data of bending moment with constant load, which is 10 Newton and 20 Newton, but with a different distance, which is from P1, P2, and P3. So based on the table, we have the reading for balance reading, net force for load at P1, P2, and P3, bending moment, and theoretical value. As we observe, the value of balance reading increased with load. For balance reading, we have to take a reading at the spring balance when load is applied, and for net force, in order to get the value, we have to subtract the current balance reading with initial balance reading. Subsequently, same goes to P2 and P3. For bending moment, we use a formula to get the value, and for theoretical, we use free body diagram to get the value for theoretical value.
So the next is the table for part 2, which is the different load. So you can see that we change the load for P2 equal to 5 and the other part is P1 and P3 equal to 10 Newton and P2 equal to 5 Newton. So we make the calculation for bending moment on the experimental value and also the bending moment for the theoretical value, and we got this data.
So these are the free body diagram needed for calculation. For we have FBD1 and FBD2. For FBD1, it is used to calculate moment at point B, and FBD2 is used to calculate moment at point C. We also recorded the distance A from the distance A to P1, P2, P3, and B, which is for P1 is 150 mm, for P2 300 mm, P3 650, and B 900 mm. Here are the examples of calculations for part 1. We have to calculate the experimental bending moment and theoretical bending moment. For experimental bending moment, we have to use a formula which is net force multiplied by lever arm of 150 mm, and we obtain the value. For theoretical bending moment, we have to use the free body diagram to calculate the moment at point B and point C. Using formula, moment equals to force multiplied by distance for P1, P2, and P3. For distance P1 to B, we have to multiply the force, which is 10 Newton, with the distance for P1 to B. We substitute into the equation and we get the value for RA, which is to be used to calculate the moment at point C. We substitute the RA into equation for moment at point C and we obtain the value for moment. We have to use the same steps for calculation for load 20 Newton.
This is the examples of calculation for part 2, which we change the load but we keep the distance between the position of the load. So first we need to find the balance reading. Use the formula of value load stated above, which come from the spring balance, minus with value load of the 0 Newton. So we got the value of 90 Newton. Then we proceed to find the experimental value of bending moment. So we need to times the net force with lever arm of 150 mm, and we got the answer for experimental value. To find the theoretical value of bending moment, we need to do the formula of moment, summation of MB equal to 0. Then we substitute the value to find the RA. Once we got the value of RA, so we put the value into the summation of MC equal to 0. And then we got the answer for the theoretical value of bending moment. This is the examples of calculations for part 3. First, we need to find the balance rating. The formula is the value load stated in the table for the applied load, which we got from the spring balance, and minus with the value load 0 Newton. And then we will got the answer of 19 Newton. Then we proceed to find the experimental value of bending moment. The formula is the net force times with the lever arm of 150 mm. And we will got the value of the experimental bending moment. So the last part, to find the theoretical value of bending moment, we need to do the summation of MB equal to 0, which is the formula of the moment. So we substitute the value to find the reaction of A. Then the last is we need to do the summation of MC and substitute the value from the RA into the equation, and we will got the answer of the theoretical value.
According to the graph, bending moment is directly proportional to the load added, which are 10 Newton and 20 Newton. The value of bending moment is twice as it was with the initial load. The value of experimental bending moment for P1 and P2 is approximately the same as its theoretical value, but from P3, a huge difference can be seen for the experimental and theoretical value that we have calculated, which are in range of more than 50%, from 1 to 50%. The huge difference might be resulted from human error and parallax errors. For example, we obtain 1200 Newton millimeter for the load of 10 Newton at P1, while the supposed theoretical value should be 1000 Newton over millimeter. Then for load of 20 Newton at P1, we obtain the value of 2100 Newton over millimeter, while the theoretical value is 2001 Newton over millimeter. So we can observe that both value double once the load was double on both experimental and theoretical value.
This is the graph for part 2. This graph shows that the experimental and theoretical value of bending moment will increases linearly as the load increases. So the bending moment value increases as we change the value of load from P2 equal to 5 Newton to P1 and P3 equal to 10 Newton and also P2 equal to 5 Newton. This is the graph of the experimental value and theoretical value of bending moment versus the various loads in part 3. As you can see, we still got the same relationship, which is the experimental value and theoretical value of bending moment increases linearly as the various loads applied. The next discussion part is about the graph. Based on the theoretical value from part 1, the bending moment is directly proportional to the load applied. When the load is doubled, the value of bending moment also doubled, and all of the data is displayed in graphs. And those graphs indicate that the theoretical bending moment shows a linear relationship with the load, meaning that its value increases as the applied load increases and decreases as the applied load decreases. This also indicates that the ratio corresponding to the change in the theoretical bending moment value is the same as the ratio corresponding to the change in the applied load value. For the discussion part, to compare the value of theoretical value of bending moment and the experimental value, we need to find the percentage error. So the formula of percentage error is theoretical value minus with experimental value and divided by theoretical value times with 100. So, as you can see, the average range of the percentage error is between 0% to 5%. Then there are unusual range at P3 in part 1 with 10 Newton and also 20 Newton. You can see at P3, which is the value of 66.25 and also 71.87. The value is actually higher than the value of other loads. This might be from the error occurred during the experiment, such as parallax error and also systematic error. So parallax error happen when the observer eye reaches the spring balance incorrectly, and while the systematic error happen because of the misalignment of hanger on the beam, which will cause the inaccuracies of the data taken. And the last part, failing to balance the beam perfectly also will contribute to the error.
Now let's go to the conclusion. So the goal of this experiment is to investigate how different forces give impact on bending moment in the beam, and the results indicate a linear relationship between bending moment and applied loads. The experimental and theoretical bending moments exhibit a perfect linear connection with applied load, with very little variance in bending moment values. We compared the experimental value with theoretical, and it can be seen that there is a slight difference in the value due to numerous errors, such as human error that occurred during the experiment. Some recommendations suggested to enhance the experiment's result is by ensuring that the load must be stationary before taking a reading and making sure eye is perpendicular to the scale of spring balance when taking the reading to avoid parallax error. Since the percentage error is still below 100%, we considered this experiment as a successful experiment. The next one is safety procedures. The first one is ensure eyes are perpendicular to the scale, which in this case is spring balance, to avoid parallax error. Second one, use a more precise spring balance before starting the experiment. The third one, the loads must be handled carefully to prevent any injuries during the experiment. The last one is apply loads within the designated limit to prevent deformation of the spring. The last one is references. So these are the references that we refer to do this lab report.